Alright, I should be back now. Do you guys see me? Alright, thank you. Yeah, sorry. I'm definitely here. I just had to do something real quick. Thank you. Alright, let's see here. All right, good morning, everybody. Welcome to the stream. Happy Friday Eve to you guys. Yes, that's right. I said it. It's Friday Eve. Can you believe it? I can't. Let me go ahead and get set up here. I did run into a little bit of an issue there, so I just had to fix something. But while we're waiting for everyone to hop in here, I'm going to go ahead and make some files for us to work with today. And we'll begin our brief review of last time, and then we're going to jump into pointers today, okay? The most important thing. Now, yesterday, some of you may have seen, some of you may have not. Don't worry, I wasn't going to let everyone know. I did upload the next assignment. Now, most of you, if not all of you, unless you've taken this class before, can't get started on that assignment yet, okay? So, don't worry that you didn't know about it. I wasn't going to tell you anyway. I just wanted to get it up there so it's ready to go for today. All right. Now, it is the musical chairs assignment. I did make a video about it before class today. That's kind of what I was working on. So I will have a YouTube video for that uploaded right after class. And it should be a fun one. I've given you a week to do it. It shouldn't be very hard. If I have some time at the end of class, I will go over it. But like I said, I did make a video. Today, our main goals, let me just kind of put it down here somewhere. We're going to keep the operators down here at the bottom. But our main goals for today will be to go over a few things. For one, we're going to go over pointers. And with pointers, we're going to talk about what new and delete do. We're also going to go over val grind. Those are our main goals for today. I don't think it'll be very hard. I've given you most of the hard stuff. All right, there's a bunch of classes. I gave you the skeleton. So, you don't actually have to, you don't have to, type out the function skeletons or even the class. I kind of gave that stuff all to you. I basically am just making you put in the code for every function for 2 of the classes. And, it's just all of the pointer stuff. And then I make you do one little thing in the musical chairs class because I do want you to have a little bit of fun. PDF is a good one, should be. All right, so I think we're good to go. I do want to pull up my notes just so I don't get off track. Thank you for the PDF compliment. Where are we here? All right. All right, let's see. All right, that looks pretty good. So, last time we talked almost completely about addresses, okay? Now, a lot of the stuff that I talked about last time was more just for your understanding of what addresses are. Today, we're actually going to be using them. All right, so like I said, a lot of the stuff we talked about last class you probably looked at and was like, why are we doing this? Well, we're going to kind of get to that today. Just want to make sure you know what I'm talking about and how these things work. So we briefly talked about explicit conversions. I will be going over that today. Right, I gave you the actual notes for that, but I'll show you why I'm using them. That'll be in today's example. But then we talked about addresses. So to briefly cover that again, remember that addresses go in bytes. All right, they go by byte. That means each memory location is 8 bits from the next one. And the operating system can only give you 1 byte at the smallest. It will never just give you a bit. It'll give you a byte. All right. All addresses are represented as hex numbers. Right? It's just a number. It just has more symbols. Just has more symbols than the rest of, say, a decimal system or binary system. So here's your example address. Remember, all of them have this 0x up front. And all variables have addresses. Remember, can we see the address of that variable? Yes, we can. Now, I'm not going to compile this code, but just to get us started, just to briefly remind you of what these things look like. If I were to declare what I would call a static runtime variable, now you don't put static up front, it's just index, I can see what address that x is, or what address x is at by using the AND operator, right? That's the address of operator, and we talked about that last class. So that's what we use for that. And I'm keeping all of the operators down here, just so they're in a nice kind of spot in the notes. You can go reference them. All right. Now, I talked about these static runtimes variables, right? That's just any variable declared in main scope or globally, and the address will not change during the runtime. That's why we call it a static runtime variable. Let's see how I messed this up. Now, remember that the operating system is responsible for giving memory to your program. And so with the static runtime ones, when you compile your program, the compiler will automatically put in code to request memory from the operating system. Today we'll be learning about dynamic variables, where we will actually request memory from the operating system during the runtime. So the compiler's not going to automatically do it for us. We're going to do it ourselves. That's what a pointer is for. Remember, you cannot control the address you get. You can type in an address if you want, but chances are it's going to be an illegal access, which is very bad, in which you're going around in your RAM and using memory that doesn't belong to your program. So say, you know, I don't know what world this would be, but say you've got like a family server. All right, your dad or mom is like some crazy engineer, and they've just got this huge machine in the center of the house. And all of you just like remote connect to it on your own accounts. So you're all playing on the same computer at once. So you're working on your homework and your brother's playing Minecraft. And you start illegally accessing RAM on that server. You might change your brother's Minecraft game, because you go in there and you'll access some of the memory that he's using. So you can't do that, but you're not allowed to. And we'll talk about how you can find those errors in your programs today. All right. And then lastly, kind of, at least for addresses, how do we get the value stored at that address? Well, we're going to use the dereference operator. Now, in this case, this is pretty redundant, right? If I wanted to dereference this address, why wouldn't I just type X? Well, today we're going to learn about pointers, okay? So when we use a pointer, we have to dereference it, all right? We have to dereference it. So obviously, I'm just going to repeat what I said. This doesn't make much sense, right? And in fact, if you're just completely evil, you can repeatedly do this over and over again. In fact, I don't even think you need the parentheses. I just kind of do that to show you. I can just keep doing this over and over and over again. Okay, I can get the address, dereference it, get the address, dereference, get the address, dereference, so on and so forth. Okay, so that's just some basic address stuff. Now, I briefly talked about arrays. All right, I just want you to know how they work. All right, so remember, arrays are only passed by reference. Why is that? Well, arrays are addresses. In some sense, they are pointers. And then winky face, smiley face. I like the winky face. They are pointers. Addresses are arrays. Here we go again. Arrays are just pointers, just so you know. And that's why they're passed by reference, right? I told you that when I opened that code and I said, hey, my int x of array size 3 is equal to this, and then I come down here and I see out x, what do we see? This prints some address. This says, hey, this is 0x004, something like that. All right? So, what the heck does doing this, what does that mean? You guys remember, what does that mean? Well, we know that the brackets are an operator, and they are doing something. They are dereferencing this. Now, can anyone tell me what the equivalent of this is? And as I think Pig said last time, why would we do this? Well, there's really no reason. I just want you to know how this works. It is a binary dereference. What is the equivalent code for this? This is a test question that I'll ask you. I'll say, please access the first element in this array using 2 different methods. That's a test question I will ask you. So what is the equivalent of that, but not using the binary dereference operator, rather using the unary dereference operator, right? Yes, you guys are paying attention. Thank you. Okay, so these are the same things. Basically, this says, this is my address x. Let's add 1 times however many bytes this is. Say that ints are 4 bytes. So this +1 is gonna add 1 times 4 bytes to that address, and then it will dereference it. And that's because arrays are contiguous in memory, right? So we talked about that, right? What does it mean to be contiguous? They're side by side. So dynamic and static arrays are contiguous in memory. So by using the starting address, we can add X number of bytes to get the next element. All right. And remember, we started talking about data types. Why does this matter? Well, different data types have different sizes. All right, they have different sizes. So can we tell the size of a type? Yes, we can. We use this size of operator. Now, chances are you're never really going to use this, just like in your program, unless you're typing a C code. In this class, we learned C++, but in C, you know, if you ever take an operating systems class, you'll use this size of thing. But just so you know, I'm going to put in parentheses, not really used in C++, okay? It's not really used in C++. But you can, you know, if you're ever wondering, say you declare your own class. You say, hey, my class musical chairs, how big is it? You'll type size of musical chairs. It'll tell you exactly how many bytes that is. All right? And so, just so you know, when I'm talking about this binary dereference operator, which we talked about, it will give you the value stored in an address plus offset I. I basically gave all this stuff to you. So the formula for that is, if we were going to say address, let's say we have an int x here, array, I don't know, say 3, like always, and that's equal to, say, something up here. So when we say x plus 1 in C++, it does this. It will take the address of x, which is x, plus 1 times the size of an int to get a new address. So that's what it means, right? That's what it means. So what does this evaluate to? Can anyone tell me? Meaning, obviously, x is going to be x, but what is the size of an int? 4, right? So that's going to be bytes. It's going to add 4 bytes to that address. So let's pretend we're doing, say, just a double and a char. I just want to make sure we know this. I know I'm kind of repeating myself, but this is important stuff, I promise. Say we're doing a char. Let's say we're doing a double. We do an x plus 1 in C++. So what does that come out as? It's x plus, say, 1 times. How many bytes for a character? 1, right? It's going to be 1 times 1 byte. Bytes. All right. And then finally for a double, it's going to be 1 times how many bytes? 8. So we understand this? That the compiler C++, whatever, the runtime, it's all going to just look at the size of that address. So that's going to bring us into our pointers talk. So the next thing we need to talk about, did I say W? W. Sounds French or something. All right. So we're going to get into our pointers talk now. So the first thing I need to say is all addresses have a type. All addresses have a type. We say, yeah, well, they're a hex number, obviously, but it's more than that. The address contains what type it's holding, basically. So the address's type is saying, I'm holding an int here, or I'm holding a double. So basically that question it asks is, what data type am I holding at this address? All right, so now we're going to have a little bit of fun with C++. And this brings us into pointers. So we're going to do that real quick. Now a pointer I'm sure you guys have heard horror stories about pointers. I don't know, with everything being remote. I don't know how many friends you talk to, but I do remember when I was in CS135, all my CS202 friends were telling me about how scary the pointer is. But I promise you, pointers are not scary. It might just be a little bit confusing up front. So pointers are variables that hold addresses. So they don't hold the actual value, right? You'd say int x equals 3. You would say, hey, that x holds 3. And then if you wanted to get its address, you would need to use that ampersand. Well, with a pointer, it just holds an address. All right? So pointers hold addresses, and pointers have types. A few other things about pointers. Pointers are used pretty much exclusively for dynamic variables. So what do I mean by that? Well, let's say you're writing a program that's going to hold any size of data. So for example, let's say you are working at a company that processes COVID data. And the data comes in every morning in a CSV file. Does anyone know what a CSV file is? You know what that stands for? What's the CSV file? Someone say yes. What's a CSV file? What does it stand for? Comma separated values, right? It's an Excel sheet. And so that COVID data will come in every day, and you don't know how many rows are in that CSV file. You don't know how many rows are in there. And so your program needs to be equipped to handle that. And with your CS135 knowledge, you would say, I'm just going to declare an array of 10,000. And hopefully that handles it. Well, one day the COVID file comes in and there's 10,001 rows in it. And what does your program do? It'll probably start writing to illegal memory. Maybe it's seg faults. Something like that happens. And so we need a way to have dynamic variables, meaning today, I only need 10,000 rows of data. The next day, I only need 200 rows of data. So pointers are used almost exclusively for dynamic variables. All right, so size of data may be unknown, in which we need to request memory from the OS during runtime. Now, guess what? You're taking C++ class at UNLV. What programming language do we teach you guys first here at UNLV? It's C++. At any other university, not all of them, but you might learn Java, you might learn Python, and guess what? Java and Python do this all automatically for you. But we're the C++ guys. We're the systems engineers. And we're going to learn how to do that stuff ourselves. So Top Wolf talks about vectors. Some of you learned in 135. Do you know what a vector is? Well, obviously it's a dynamic array, but I'm going to let you guys in on a little secret. It's a variable size array. Are you talking about Victor? I don't know. You know what a vector is, Top Wolf? It's this. Let's say it's for ints. It's a class that someone made that has a pointer in it. So yeah, you could use a vector if you wanted to, but you need to learn how that thing works. And I tell you how that thing works. Someone made a class vector, and inside of it, it has a pointer. That's what a vector is. All right? You know what a string is? A string, you know how a string size can just continuously change? You can add things onto it. You can take things out of it. A string is a character array. What's inside that class string? Well, it's a char pointer. And during the runtime, it says, hey, OS, I need some more memory for my string. Or it says, hey, OS, I don't need this much memory anymore. So I hope that kind of enlightens you a little bit, okay? That, yeah, you can import these things if you want, but they work with exactly what I'm teaching you today. All right? So, I guess first we need to talk about how pointers work. Well, the syntax of a pointer. A pointer is declared with a type and the star. So example of that. Well, the syntax for that, of course, will be, say, type. Now, you can put the star anywhere in here. You'll see me do this as much as I possibly can. I like to put it over here next to the variable name. But you can put it there. You can put it like this. It really doesn't matter. This is a little confusing because it looks like you're multiplying a type by a pointer. But the star needs to be there, okay? I'll always put it there. That's how I do it. That's how I recommend you would do it. And there's a reason I do that, and I can't remember it right now, but we'll run into it today while we're coding the example, I assure you. So if I were to give you an example of that, if we wanted an integer pointer, we would do this. If I wanted a character pointer, I would do this. If I wanted a double pointer, I would do this. So let's go look at that in the code. All right, the only thing required here is the star. That's a little confusing, right? Because we just learned that this is a dereference operator. It's also a multiplication operator. Like, come on, C++, what's up with all this ambiguity? Pick one thing and use it. Well, at the same time, there's not enough keys on our keyboard, is there? So that's a problem. So let's pretend we say we have int x up here, and then down here I say, hi, I want this int pointer, I'm going to call it an I pointer, and I want it to be equal to this. Now that won't work, right? Why won't this work? I've told you why it won't work, kind of. You're just going to have to use your thinking brains here. Why is this not allowed? What does a pointer hold? Similarly, this won't work either. 4 isn't an address, right? X is also not an address. So, what if I wanted I pointer to maybe contain X, what can I do here? Yes, exactly. Now that'll work. Now it says, hey, I'm okay with that. Now this, you won't be doing this very much, all right? This is just me showing you how it works. So you can see out X. You can see out the I pointer. You can see out the address of X. And you can see out the dereferenced version of the I pointer. All right. So this is our static runtime variable. This is our pointer. This is our address of X. And this is our deref pointer. All right. So we're going to see probably 4 here, some address, and then we should see 4 here. All right, let's run that. Now I'm gonna mess up your brains a little bit. So prepare for brain mess up. I guess. English good. Here we are. Okay. I don't need to clear again. I just like to do that all the time. C++ 11 pointers.cpp. All right, and we'll run it. What do you know? Same address, same value. Now, time to think a little bit. Let's say I do this. I'm not going to worry about printing the X. I'm not going to worry about printing the I pointer. Let's just pretend we're going to print the pointer. And then somewhere down here I say, you know what? X now equals 10. What prints on line 15? What prints on line 15? Top Wolf says 4. Chef says 10. Now, Uchu, it's not an address because it's dereferenced here. Recall that this will print the address here. This will print the address up here. But if it's a pointer and we dereference it with our operator, I'll even put it in parentheses here to kind of indicate that we're doing something to it. We're going to get that value. So a lot of you say 4 and some of you are saying 10. Well, let's run the code. Let's see. It's 10. You might say, why is that? Well, X and I pointer are kind of the same. Yeah, it's kind of the same variable. All right, it's what we call this is an alias. Swift says it's because it's connected to the address. We call this an alias, in which two variables are working with the exact same address in the memory. So up here, I say, hey, pointer, you are looking at X. You want to get out a paint diagram here? What do you say? I think that's the one I want. Oh, we lost it. It was paint, guys. This time it was paint. Paint got us. How dare you, paint? I can't believe it. I trusted you to use little resources. And yet it got me. Wow. Yeah, paint is just not responding. As I told you guys, I still haven't cleaned my computer. I really need to get on that. All right, everybody. Wow, that's a big thing. So we have X equals 0. Now, what do you say? Do you guys like this? Is that nicer? So somewhere here in memory, we've got a 0. My face in the way? I don't think so. Dark mode. All right. Somewhere here we've got 0, 0x, 0, 0a, something like that. All right, that's our memory address. And I'm going to make myself real small. How's this? Why can't I move it? Hey. Oh, there we go. See ya. Okay. So, we've got an address here. Somewhere in the memory it's contained 0. Now, X, this is X, by the way. All right? X is looking at this. In some sense, it is X. I just kind of want to put that in there. In some sense, this is X. All right? This is X. And then, somewhere over here, I say, I want an int PTR. And I say, what is this? Whoops. What do I say? I say, hey, this is equal to X. I'm working with too big of letters here. You know, when you're like making a big sign and you start writing the words all big and then they get smaller towards the end? That's what's happening right now. I say, hey, this pointer is equal to the address of X. So now what's it doing? Well, it says, hey, I'm looking here. I'm looking at the same memory. I'm looking at the same memory. So when I change this value, I'm changing both of them. Is that clear? Does that make sense? We've made an alias. That's what that does. All right. So now I'll come back to real size. All right, folks. All right. So that's what that does, all right? That's what that does. So now we're going to open up a piece in our notes. Called memory. I'm going to just call them memory things to look out for. Fuzzy asks, if pointer was just X, it would print out as 4? What do you mean? If I said this? Is that what you're asking? If I just said that? Two or more variables. Well, lucky for you, the compiler won't let you do that. But if you could somehow convert this, let's say, to an in pointer, yes. I put that on the wrong side. Let's see if that works. So, well, I talked about this thing yesterday. What is this called? What did I just do? What is that called? Anyone tell me? What is that called? Let's check it out. What is that thing called? It's called an explicit conversion. So I get a warning here, but it's still still compiled. Oh, okay. What happened here? Well, look. Fuzzy, I hope this answers your question. I converted 4 to an integer pointer. I said, this is memory. So yeah, here's a memory address. And then I tried to dereference it. Now, I got a seg fault, and the reason for that is I tried to dereference an address that probably doesn't exist. I'm not sure exactly where RAM starts. This might be out of bounds. I'm not sure. All right, but I tried to dereference an address that was not mine. In fact, I tried to dereference an address that doesn't belong. That's like, this address doesn't even exist. So Siptos, you said illegal access? Almost. But more so that this address is probably not even a thing. This address probably doesn't exist. Now, if I tried to dereference, say, an address from another program, let's look at this, for example. Let's look at this. We'll go over that later. Let's look at this. I'm not going to dereference it yet, but let's say I do this. I'm gonna grab this address here, okay? I'm just gonna grab it and save it. Yeah, I'm aware. All right, here it is. I should be able to come up here and say, hey, you are equal to that. Now it should work. Yeah. So Pig, does that? What are you doing? What are you telling me here? You jerk. Maybe I have to convert it. Yeah, I could do that. Hopefully that answers your question. Now, I should be able to dereference it. Now, this time, do you think I'll get a seg fault or not? Do you think I'll get a seg fault or not? What do you think? All right, that one worked. Are we going to get a seg fault here? No. All right, I kind of like that answer. Oh, hey, stop that. I guess we are getting a seg fault. Now, here's what I would say. I'm sorry that I steered you wrong. Not in every case do you get a seg fault. In not every case will you get a seg fault. I didn't expect this to seg fault. I didn't expect it to. But it seems to... My computer seems to have a lock on my memory. But let me just show you this. Recall if I were to do something like this. If I said, hey... Because just all I'm saying is we know this exists in my memory somewhere. And so I would say the behavior is undefined. If I say, you know, int y, an array, right, of size 2, and I say equal here. I don't know, 2, 2. Now we're going to assume that this 0x003 starts here. And so the next location is going to be at 0x00, maybe 7, 3, 4, 5, 6. Yeah. And then if I access this at, say, 2, I don't think I'll get a seg fault here. But this address here, whatever I'm accessing, is not allocated to us. So, you know, I'm disappointed that this digs... I don't know if I'm disappointed or not. You can't expect it to do that every time. That's all I'm saying. Do you guys understand what I'm saying? Is that the behavior is undefined. And you should never really try to do this in your program. All right? Sometimes it'll seg fault. Sometimes it won't. You just have to be aware of what you're doing. So let's get back here to our stuff. So alias. 2 or more variables are looking at the same address. Your disappointment is immeasurable. All right, 2 or more variables are looking at the same address. Now, this is sometimes bad. Not always. Example, linked lists. Now we'll get to linked lists at the end of the semester, okay? Did you lose me? I don't think so. That's what the F in the chat is for, right? When you lose me. Now, next things we need to talk about is, let's see, dangling pointer and a memory leak. Oh, okay. So we'll get to that. Now, what we need to talk about now is actually allocating memory from the operating system. Whoop, hit my microphone there. Sorry about that. So, how do we allocate memory? So, when I say allocate, what do I mean by this? I say, hey, request memory from the OS. Now, what do I say when I say deallocate? I say give memory back to OS. All right. Say, please give me some memory. You can have this back. I don't need it anymore. So to allocate, step 1 is we need a pointer. Step 2, call new. All right, so we're going to go down to our operators now. I guess these are more considered functions, but yeah, I guess I'll call them functions. I think if you go look at the operators page, they might be called operators, but we're just going to call them memory functions because I like it better. They're called like functions in C. So the first one we have is new. So how do we use that? Well, what does it do? Well, it will request X amount of bytes. X amount of bytes from the OS and return the starting address. Okay? So we need a type. So if we're going to do some syntax here, if we want to request memory for a single variable, it's going to look like this. Type pointer equals to new type. All right. Now, if we want to do, that's for a single. It's for a single var. And in your assignment, you're only going to be working with single variables, okay? In assignment 5, you'll work with the arrays, but not quite yet. If you want to do an array, it's going to be new type, say some value size. All right, and that is for an array. So you can use new in 2 different ways. One to request an array, and one to request a single variable. Remember, new returns the starting address of whatever we got. All right, it's going to put that address in the pointer. So let's go ahead and look at that, shall we? I'll also give you an example, not only in the code, but here. So if I want an int pointer, and I say equals new int, how many bytes do I get from the operating system? Can you tell me? And then I'll do another example. Here. In this case, how many bytes do I get from the operating system? And in this case, how many bytes do I get from the operating system? Yeah, we're going to get 4 bytes here. Now, what about this one? How many bytes we're going to get? How many bytes does the operating system give us here? 4 times 8, right? 32. 32 bytes here. Right? Very good, very good. So, that's what new does. That's what new does. Now, this array is guaranteed to be ours. Or this address is guaranteed to be ours. So, the address returned now belongs to the program. Meaning the operating system will try to protect it for you. It will say, I'm not going to give this out to anybody else. Someone might try to access it for you, but it's not always going to happen here. All right. So let's mess with it. Equals new int. Now, if you wanted to do this, this is fine as well. All right, it works just like that. This returns an address, okay? It returns an address. So as long as you're storing it somewhere, doesn't matter if you're doing it right off the bat or if you assign it somewhere later. Now, before we move any further and I show you some crazy stuff, I'm gonna say this because it's very important. When a pointer is declared, or iOS, when pointer is declared, or when the pointer is not supposed to be holding an address, put null pointer inside of it. Store null pointer inside. All right? When a pointer is declared, or when the pointer is not supposed to have an address in it, store null pointer inside. Now, why is this? Look at this here. This requests, this is confusing, okay? This is a static runtime pointer variable. All right? So in some sense, the compiler, the computer, it will give you enough memory to store an address. All right? So it goes in the memory and says, here's enough bytes to store an address. An address that contains an address. Right? Okay. So is this always guaranteed to contain null pointer? What do you guys think? Is this always guaranteed to contain an address that will seg fault on us? Is this always guaranteed to contain null pointer or 0 or whatever the default value is? No, it's not. There could be junk value in here. There could be a rogue address sitting in here. There could be a rogue address sitting in here. So we say, hey, you better be null pointer. Okay? Yes. You better be null pointer, all right? I am not going to try to dereference you by accident. All right, so that's what we do there. This means it's empty. A random homeless value, yeah. Null pointer means empty, okay? Means empty. Means empty. Now here's a fun little fact for you. When does your program segfault? Either when you dereference an address that doesn't exist, or, I don't know, dereference that you're not allowed to, or you deref a null pointer. So Synthos asks, isn't it kind of initializing a variable, but instead of a junk value, it's a junk address? Yes. Now, Mail asks a good question. Couldn't you do null by backslash? All right, the backslash n is an n line. The backslash n is an n line. This is the null character. That's your null character. Now, here's the thing. You could do it, but you just have to recall these things. This is essentially equal to an integer 0, which is also equal to null pointer, which is also equal to false, which is also equal to, I'm going to stop there. In memory, everything is represented by a number. All right? Everything is represented by a number. And you know that 0 is represented the same way that false is represented, the same way that null pointer is represented, the same way as null character. You can pull up the ASCII table and look and go find that null pointer. And it's the 0. It's the very first thing on there. It's the 0. So yeah, you could do it. Please don't, though, because it's confusing. Only do that for a character. I would very much recommend doing this. It's like the same thing as doing this. Someone's going to go, why did you do that? That's an int, and that's false, right? So you could do it. Please don't, though. Hopefully that answers your question. Synthos asks, isn't kind of initializing a variable, but instead of a junk value, it's a junk address? Yes, it is a junk address. So this will give us some stuff from the memory, all right? This gives us some stuff. If we wanted to, we could say, hey, iPointer now equals, well, let's see what we get. First thing we're going to get is some address. So let me go ahead and print it out. And then let me dereference it. And then we're about to have some real fun. Everyone's with me so far, right? I haven't lost you. Pointers, not so scary yet. All right. So, the operating system gave us an address there. And what was stored at that address looks like it was 0. Looks like it was 0. Yeah, it's a lot to grasp, but you're going to get some fun practice. We're going to use them for the rest of this class. Thank you for the feedback. Obviously, we have some delay there, and like I said, I'm sorry about that. Deborah strikes again. Now, this is... You're confused. Well, please ask questions or come to office hours if you need to. Now, there's something that I did that's wrong here. Does anyone know what's bad about this program? It's mostly right. This program is mostly correct, but there's something wrong with it. Does anyone know what I said? Or I kind of mentioned it earlier. What is wrong with this program? Is there anything wrong? Obviously, it's compiling and it's working, right? So what's wrong with it? Ha! Chef is right. Yeah. Chef is right. So we'll get to that. So as you'd expect, just so you know, I can assign values to that pointer by dereferencing it. All right, so I can put 10 there. Now, Chef said exactly what happened. I didn't put my name up top. Yeah, you're right. You're right. I don't know if you noticed, but in the auto tests, I sometimes take those out. If I make the auto test, I take them out because I don't think it's super important. It is when you're working, like in a you know, if you're ever working somewhere, you're definitely going to want to put your name on it. But for your homeworks, I really don't care. Anyway, I didn't deallocate it. So what does this mean? When I call new, I get the address, but then I never tell the operating system that I'm done with it. So we come down here, we return 0, program exits, OS still thinks program X has the address. Now guess what? This address is kind of lost forever until the system restarts. There are ways that the operating system will reclaim the address, but for the near future, this address that I've requested from Bobby, wherever it is, Bobby will not be able to give this address out until it runs a garbage collection algorithm or the system restarts. This address is now lost for the near future. I never returned this address to the operating system. Bobby still thinks that this has been allocated somewhere. Now we use a program called valgrind to tell these things. Uchu says if you run the program over and over, you will get a seg fault eventually. Not a seg fault, but if I request too much memory from the operating system, eventually the program, like the operating system, will say, I don't have any more memory to give, and it will terminate your program. That's called a bad allocation. So to answer your question, you can only request so much memory. I wouldn't say a seg fault, but the program will break. It will break. Yeah, so once you allocate memory, you need to deallocate it. So check this out. We're going to use this program called valgrind. I'll put it in the notes. And whenever I run valgrind, it tells me everything that I did wrong memory-wise with my program. So what I type is valgrind -- leak - check equals full. I'll put this in the notes, and I run it with my ./a.out. It kind of looks like that. And look what it tells me here at the end. It says, hey, you definitely lost 4 bytes. The 1 block means the request. So I requested 1 block of 4 bytes. I lost 4 bytes. There's a memory leak here. So what do we call that? I just said it. It's a memory leak. So here's the memory leak. This is address is overwritten or program exits before address is returned. So what does this mean? How do we fix it? Well, for every new, you have to have a delete. For every new, you need to have a delete. That's how we fix it. For every new, you need to have a delete. All right? So that brings us to our next thing. How do we deallocate memory? Well, we call delete. So who said that? Top Wolf, I think. Someone said. Let me see here. I got to give... Chef said that, right? Yeah, Chef said that. We need a delete keyword. Sorry about that. So we type delete here. And how does that work? Well, yeah, I'm sorry. Your names are the same color for me. So I'm associating the color of the name with the person. I'm sorry to give credit or whatever. I'm just doing my best over here, guys. This will return X amount of bytes to the OS. Okay? And the address returned no longer belongs to the program. What? All right, so what's our syntax for that? Well, pretty simple. We either type delete pointer. All right, that's for a single variable. Or we type delete brackets pointer. That's for an array. All right, that's it. That is it. So if we do the example here, just like up above, I'm going to type, say, delete pointer for the int, and for the double pointer, I'm going to type delete brackets dptr. All right, that's it. So how do we fix that? Well, we go on our code, and we say, hey, I'm done with this now. You can have it back. That returns it. So we'll take our pointer here. We will compile it. We will run it with valgrind. And look, heap summary. All heap blocks were freed. No leaks are possible. You can't really see it because of my face. So see you later. All heap blocks were freed. No leaks are possible. Now you can get valgrind to tell you what's going on. You want to see that? You should do it. I actually went over this in the assignment video too. So if you need a refresher or you don't want to write it down, I'll put it in the notes. It's in the video. It'll be in this video. It's everywhere. You have no reason not to find your memory problems. So let's say that I remove that delete. Now I've created a memory leak. I load that to Bobby. I compile it. And what I want valgrind to do is tell me where my problem is. Well, the first thing I need to do is compile with a -G. This puts in debug symbols. This will tell me the line numbers that we're working with. -G. And now when I run valgrind, you will see somewhere operator new was called where? Pointers.cpp line 9. So I'll go look at line 9. Here it is. And so it's not telling, this is as far as it knows, right? It says you allocated this, you never deleted it. So you kind of have to go figure this out. You have to say, oh man, I allocated this and then I lost it. Here's another example of a memory leak. So tell me, what do you think? I deleted it. What's wrong with this program? I deleted it. What's wrong? What is wrong with this program? I deleted it. I should be right? This program should be fine. There's no problems. What is my issue? What is my issue? And I said it. I said it in the notes. There are 2 pointers. Yeah, kinda. Now it says, is it still sharing the address? Well, look, this gets an address. This is now 0. This is, say, 0x003. And then this goes, here's a new one, 0x006. Is there any way that I can reference this again? Is there any way that I can remember what 0x003 is? So some of you are saying it tries to delete both. It deletes the first one. It doesn't know which one I'm talking about. Well, this is like any other variable. This is like any other variable. At this point, what is this value? At this point, what does this pointer contain? It contains 0x006. So which one does it delete? The one that it knows. So it does know what it's talking about. It says you're going to delete this one. But what about this one? Did this ever get deallocated? No. Is there any way that we can get back to it? No. Here we lost it. It's been lost. 0x003 has been lost. It doesn't know it anymore. And so when you're running your code, you're in here, you run it, you compile it, you val grind it. It says you lost it. Klaus, you're exactly right. Klaus, you're exactly right. Look, it's telling me pointers.cpp line 9. What is it saying in there? Well, it's saying that this never got deallocated. And I said it in the notes. Listen. Listen. Didn't I say it in the notes? I swear I did. I swear. Maybe I didn't. For every new, you need to have a delete. For every new, you need to have a delete. And yes, you're right. This is a memory leak. Address is overwritten or the program exits before the address is returned to memory. So for every new, there has to be a delete. Now this doesn't work. This doesn't work. The address was already deleted. Klaus was right. It needs to go up here. You need to return that address before you get a new one. Okay? Unless you use a different pointer. Yeah, so Chef says you need to delete in between the news. Yes. Or you can use 2 pointers. Will you follow this? Tell me. Will you call this? Or will you follow this? Let's say I declared another pointer here. And I say int I pointer 2. And I say now this is equal to I pointer. Now this contains 0x003. Now this contains 0x003. So now I overwrote it, but guess what? This now has the old value. This now has the old value. What did I do here? I talked about this earlier in class. What is this called? What is this called? You guys should know this. What is this called? What did I make here? What is that called? An alias, right? Yes. It's an alias. Making me so happy right now. These 2 pointers now contain the same address. But then I overwrote it, so now they're no longer aliased. Okay? So that's how that works. That's what a memory leak is. Now, I'm going to show you one more problem. We're going to do something fun, and that's going to be the rest of our class for today. Okay? That's going to be the rest of our class for today. So, tell me this. That should all work fine. Yeah, what's wrong with you? Now what's wrong with this? Or what's wrong with this? What's wrong with that? What did I do there? Why is that bad? Klaus says there's no value there anymore. I don't know about that. I would say Chef is more correct in that there's no longer an address there that belongs to you, right? It got deleted. iPointer still contains, what do we say? iPointer still contains 0x00 or 0x006, right? Still has it, but this address no longer belongs to me. This is not mine. So here I am playing with my brother's Minecraft memory again, right? Maybe the operating system sent that address to somebody else. I say, nope, you know, I'm going to mess with it. We call this a dangling pointer. Pointer contains memory that was deallocated or that does not belong to the program. Yeah, exactly. That's stuff like that might happen, right? So a dangling pointer is a pointer that contains memory that was deallocated or that does not belong to the program. How do we fix this? After every delete, this is very safe. You are null pointer. You are null pointer. Now my program will segfault, which I would much rather do than change my brother's diamond pickaxe to a stone pickaxe, right? I would much rather my program segfault than, you know, me accessing memory that's not mine. All right? At least I know now something's wrong with my program and I can go find it. If I don't do this, then the program will just run, and that's that. The program will run. You'll have an illegal access. You want to see that? Let's see an illegal access, an illegal read, and an illegal write. We should have both. We should see both here. All right, let's see. We have an invalid read of size 4 on CPP 21. On line 21, there's an invalid read. We dereferenced an address that does not belong to us. On line 22, we have an invalid write. I wrote to memory that does not belong to us. Does it make sense? So that's a dangling pointer. And valgrind tells you exactly what's going on. All right? You should always do this. Always do this. So now let's just have a little bit of fun with our remaining 10 minutes. That's pretty much all we had to talk about for the assignment. Is there any questions you want me to go over before I do just something that's a little bit fun? I'm not going to do anything that you need to remember. Well, I want you to remember it, but it's not anything I'll ask you on a test. I just want you to see it. Now, likely you guys are going to have to come, some of you are going to have to come to office hours. This stuff is a little whack, all right? This stuff is a little wacky. Stuff's a little wacky. Obviously, programming languages like Java and Python said, we're not going to leave these in people's hands. We're going to do it automatically. I don't want anyone calling new or delete. The reason it's available in C++ is because C++ is used for system programs. All right? The programming languages like Java may be too bulky. They have too many features to be run on, say, a little chip. All right? C++ is maybe not. C is pretty lightweight. It's pretty fast, and it doesn't come with many, decorations on it. It expects you to know a lot. All right? So now let's have some fun. This is gonna be my I pointer. Equals 4. All right. Oh, sorry. Whoa, that's not allowed. We have to allocate it first, and then we say, hey, my I pointer is equal to 4. All right. And here's what I always do this. As soon as I type new, I go put the delete down here. I do it right away. I don't want to forget about it. As soon as you type that new, put a delete somewhere. All right, you can move it later. Just put it there. For those of you who are developing on your own MacBooks, be careful with this stuff. You can probably just restart your computer and get that memory back. But if you write a program with an infinite loop with a new inside of it, you're going to run out of RAM on your MacBook. And then you say, Deborah caused this. No, it was you. It was you who did it. All right? So maybe if you're scared, use Bobby instead. Visual Studio, that will handle it for you. All right? Just be careful with this stuff. All right? Here you are. The world is in your hands, okay? Top Wolf, yes, you can. I would believe so, yeah. I would recommend using Bobby. You should destroy Bobby. All right? I wouldn't call it a virus. All right, so this contains 4. This contains 4. Now, I'm going to do my best here, okay? I'm going to do my best. I'm going to do my best here. 4, I think, in memory looks like it's 4 bytes. So 1234 dash 1234. I'll put it above or below. I think it does then this, and then this. But 4 is going to be, that's 1, that's 2, that's 3, that's 4. So I think your memory looks like that. Okay? That's 4. So check this out. I would like to dereference this pointer converted to a character pointer. What? Earn line. Can anyone tell me what that prints? What does that print? What does that print? Did we, I'm seeing if we understood why a pointer has a type. Why does the pointer have a type? Does anyone know what prints? So Chef, you said the ASCII value for 4. I'm okay with that, except here's one thing you need to consider. Say this is 0x00, A. No, that's too hard. That's too hard for this. So let's say that's at 0x004. This one is then the next one up, that's at 5. This one's the next one up, that's at 6. This one is at 7. All right, so if this is an integer pointer, it goes to this, the dereference will go to this address, and it says, I need 4 bytes. And it dereferences 4 bytes, and it gets a 4. Now, if I convert this to a character pointer, how many bytes is a character? How many bytes is a character? I've asked this question a million times, right? How many bytes is a character? I believe. We know this. It's 1. So look at this address. How much of it is dereferenced? How much of it is dereferenced? Are all 4 bytes dereferenced, or which one is it? And what is it? You can say the numeric value if you'd like. But what does it come out as? I assure you, it's not looking at this one. It'll never get to this one. Right? Which byte does it dereference? It dereferences this one. This pointer here contains 0x0004. If I convert this pointer to a character pointer and then dereference it, it's only going to dereference 1 byte from the starting address. This should print a null character. Now, similarly, how many bytes does this one dereference? How many bytes does this one dereference? Eight. Guess what that does? That goes out of bounds, doesn't it? It's going to read 4 additional bytes out in the middle of nowhere. There's some bytes out here, okay? There's some bytes. We don't know what they are, but they exist. It's going to read them. This is considered an invalid read. All right, this is an invalid read. It's going to read whatever these are, and then whatever that represents in a double will pop out. You want to see what this looks like as a float? Now, guess what? The float will come out. It won't be an invalid read, but it's going to look different. Floats represent their data differently than integers do. All right. They represent their data differently. What did I call it? I called this fun pointers, huh? We're having so much fun right now, aren't we? All right. 4. What did I say this prints? This prints a null character. Is that right? I think so. This only dereference this. This is a null character. Does a null character look like anything? No, it doesn't. Right? No, it doesn't. Now this is this is a double, right? It's 8 bytes. It dereferenced from that starting address. So all it did was it said, all right, these are my first 4 bytes. And whatever these are my next 4 bytes. And I come out like this. And then finally this, whatever that is, that's 0.000000000. I could keep going, right? That is a float in this version. And that's my class for today. Did we learn something? Hopefully you understand why pointers have types, why it's important, because we need to know how many bytes to dereference. Today we learned how to call new, we learned how to call delete, we learned about our memory problems, memory leaks, dangling pointers, and aliases. Okay? You have enough knowledge to do the assignment now. So please get started on that. Ask me questions if you need. We're going to have 2 more classes on pointers. Maybe just 1. 2 or 1. Well, we're going to use them for the rest of class. So just stay tuned. This video will go up on YouTube. The notes will go up. The files will go up. Best of luck to you. Thanks for coming today. Have a great weekend. I always love seeing you guys in the chat. We have such a good time. And once again, I'm sorry that my computer has a little hiccup sometimes. I'll maybe work on getting that fixed. Okay? You guys are free to go. I'll see you guys next time. Top Wolf, you're welcome. Kid, you're welcome. Yang, you're welcome. Fuzzy, have a great day. I will hydrate. Oyman, you are welcome. Synthos, you're welcome. Kane, you're welcome. Uchu, you are welcome. CS202 student, you are welcome. Giovanni, you're welcome. Chef, you have a great day. YCS, you're welcome. Cool Turbo, goodbye. Pig, you are welcome. Have a great day, guys. Thanks for coming. Brandon, you are welcome. Anybody else?